the thing that, I love this textbook. I think this textbook is well organized. The one thing that they do that I really hate, which you just found, is they talk about the force of gravity and the normal force in like the third or fourth section of the chapter, but you need to use it in the second section. So in that first problem, you're given a mass of an object and you're asked to figure out the force on the object. So for any object, you know that you are all attractive to the Earth. All objects on this planet are attractive to the Earth. And the attractive force of the Earth on that object is called force of gravity. You know all this. Well, how do you figure out what the force of gravity on an object is? Oops. The force of gravity on any object is equal to its mass times acceleration due to gravity. Okay? So if you have an object, if this is a 10.0 kg box, 10 kilogram box, the force of gravity on this box is equal to 10.0 kilograms times negative 9.81 meters per second squared. Okay? So the force of gravity on this thing is negative 981 newtons. Wait, 98.1. Decimals. Negative 98.1 newtons. Now, we briefly talked about the idea of normal force, and I'm going to draw normal force in a different color. And I said, this was the thing that I did not like. The book doesn't really, it doesn't introduce the idea of normal force until after we've needed to deal with it. So we said, if the net force is 0, how is the object moving? Describe its motion. It's not. If the net force is 0, there's no motion. There's no acceleration, or I should say there's no acceleration. Okay? You can be at constant velocity and have 0 net force. But as long as there is, F net equal to 0, means there's no acceleration. So if I have this box just sitting on a platform, is it accelerating? No, there's no acceleration. It is, and this is the line I'll use again and again, is it rise, I can draw in the platform even though we don't typically draw other things in a free body diagram. Is it rising up into the air? Is it sinking through the platform? If neither of those is true, then the forces up on it and the forces down on it are equal. Okay? So when you're given a mass and you're asked for net force, you have to remember that F sub g is equal to mg. This is the one place where I do kind of switch over. In the last chapter, your book wants to go to using g for gravity. And I've said, when we're doing velocity acceleration problems, I recommend against that. Here, I do typically shortcut that as mg, and you'll start factoring out g. I typically, however, still use it in opposition to what your book does as negative 9.81 meters per second squared. So, and last year we had I think a serious breakthrough. It was awesome with trusting the algebra and maintaining that g as negative 9.81 meters per second squared. So does that allow you to do okay, so that should allow you to do the first problem pretty easily. And we'll continue to talk about this. So what we're told is that Joe Ponder from North Carolina used his teeth to lift a pumpkin with a mass of 275 kilograms. That is a big pumpkin. Ponder has a mass of 75 kilograms. He stands with each foot on a platform and lifts the pumpkin with an attached rope. So I'm going to draw, before I draw my free body diagram, I'm going to do this. And I'm just going to I'm going to put the pumpkin, because I have different colors, I'm going to put the pumpkin there in front of him. And So just so I understand what's going on, this is not my free body diagram. This is me saying, hey, there's this guy standing there. He has 2 feet. He's got a pumpkin that he's holding. Now, here's something that you have to understand. When you pick up an object and hold that object, you and that object are now a system. So we can talk about the mass of the system as long as you and that object are connected in some way. This is why we use seatbelts in cars. When we talk about inertia and collision impact time, momentum, all that stuff. We seatbelt you into a car because then you're it's the car and you system. And when the car stops, you stop. If you're not seatbelted into the car, you're not part of the car and you system. And when the car stops, you don't stop and you go out through the windshield or something. Not something you want to experience. When he is holding this pumpkin, it is the Joe Pumpkin system. So when we look at them as one object. So when we draw our free body diagram, we're going to do this. There they are. That's Joe and the pumpkin. You know, you can get really fancy and you can do something like this and say that's Joe and the pumpkin. If you really feel crazy, you can do this, but I wouldn't recommend it because it just confuses the issue. So, you know, you're best off really kind of sticking to Joe, circle, square, whatever. That's Joe and the pumpkin. So we're given, the first thing to do is to list all forces on Joe. Okay, all known forces on Joe and the pumpkin, the Joe Pumpkin system. So we're given the mass of him and the pumpkin, and we know that for any object sitting on the earth, the force of gravity on them is equal to mg. I'm going to shrink this a little bit. Now, we're told he's standing on a platform. And since he's standing on a platform and we're told he's standing there, he's not rising up into the air spontaneously, which would be really cool, nor is he crashing down through the platform, which would be not so cool. We know that the force up has to be equal and opposite to the force down, or he would be accelerating up or down. Oops. So what do we call the force up from a platform or a surface or the floor or anything else? Normal force. So Fn, in this case, is going to equal the negative of Fg. Because it's equal, but it's opposite. So it's going to be the negative of Fg. Now, we have the tools to figure out the magnitude of Fg. So what's the mass of the Joe Pumpkin system? 75 kilograms plus, I need to move, okay, so 75 kilograms plus 275 kilograms, all times negative 9.81 meters per second squared. If you don't put those units in, you can't do dimensional analysis later. So it's really helpful to put those in. So this is our f of g. And what's the raw number for that? 3,435. No decimal. Oh, point. Sorry.
Negative 3,433.5.
33.5, sorry. Okay, and what are the units? Newtons. Okay, so if f of n is equal to the negative of this number, copy, paste, shrink, then f of n is equal to what? 433.5 newtons. Now, here's where the trick comes in. It says he is standing on 2 feet. So, we're asked for the force upward on each of his feet. It's half of the total force on him, because half of that force is exerted upwards on each of his feet. If you stand on 1 foot, all of your force is down through that 1 foot. If you stand on 2 feet, your force is divided. So, whoops, we can say something like this. Fn equals Fn1 plus Fn2, the normal force on foot 1 and the normal force on foot 2. We could probably do a better job with that. Let's see. Yeah, let me add the word foot there. Foot 1 foot 2. So if that's, and we know that the normal force on foot 1 and foot 2 are equal. Let me shrink some things here. So the normal force is equal to the normal force on foot 1 times 2, because those are equal forces on each of the feet. So now, do you have a way to write an expression for solving for the normal force on 1 foot? Yeah. Fn divided by 2 equals the normal force on foot 1. Okay. Now I know you're going, well, I know there are 2 feet. I could just divide it in half. I don't have to do all that. You're right, you don't. And on homework, you know, I'm never going to check that. What I will say, just like I've been saying, is that developing the algebraic discipline really helps, because we have some really big, really ugly algebra coming in this chapter. I had hoped, and it's not going to happen, I had hoped, there's a lab that we normally do in Chapter 4. I call it, these are a few of my favorite things, in a box. And it's usually Christmas cookies. It's the way that we sneak Christmas cookies into physics. But I have a feeling this is not going to happen before Christmas break. Usually we do it like the last day or two before break. I think we'll probably do it as these are a few of my favorite January things in a box. There are boxes, there are ropes, there are force meters. But I don't think we're going to do it before break. But building the algebra for this is really important. So it's more skill building, it's more putting it together. It's more algebra 2, in essence. Okay, questions, comments, concerns on this one? Okay, so go ahead and do number 2. It's real similar to number 1, so it's a good substitute, and we'll pick up as people have questions.